All right, last video was just a quick, super quick review of some of the basic ideas you had from grade 11 in terms of nature of magnetic fields, that type of stuff. And today what we want to do is you actually want to look at actually finding magnetic fields. We're actually look at how to actually find magnetic fields from different things. Now, the same way electric fields come from charges, gravitational fields come from masses. We've talked about this before. Magnetic fields, of course, are coming from moving charge, not just charge by themselves, but from moving charge. The charges have to be moving, and this is where, of course, electrical current kicks in. So for what you guys do, we sort of just look at electric or magnetic fields coming from wires with current going through them. Okay, so here we've got a wire, something like this. Okay, it's got some current going through it, so there's my current. All right, now, of course, the magnetic field around here makes it's like a circular shapes around it, and we can use our right-hand rule. Number one, of course, to become like this, something like that. Okay, if we did like the dots and x's, this side would be x's, this side would be dots, something like that. Okay. So what we're going to start doing is we're going to start looking at the actual way to calculate the magnetic field from a wire. Now, if we go back to the gravity stuff that you guys did way back when you guys calculated a gravitational field, you guys had Gm over r squared. When you guys calculated electric fields were kq over r squared. Very, very, very similar formulas in many, many ways. And the magnetic field one isn't necessarily all that different in terms of how it actually works. Now, there are a couple key differences, but it's some of the basic premise is the same. If we want to calculate how strong the magnetic field is from a wire, and that's the little W stands for, I like doing the magnetic field from a wire, it's really pretty straightforward in terms of some of the basic properties. Now, for gravitational fields and electric fields, both the source of the field is important. Well, for gravitational fields, you get it from mass. For electric fields, you get it from charge. Well, for magnetic fields, it's moving charge. And if we actually look at moving charge, well, that is, of course, the current. So, of course, the current is actually important. So the current is like the M or the Q in the other two expressions. The other main thing, we'll get to the constant in a little bit. The other thing that was really important was the distance. So for gravitational fields, we had the radius squared. For electric fields, we have the radius squared. And the distance, of course, is going to be important in this one too. The radius is going to be important. And same thing, the further away you get, the weaker it's going to get. But there is one key difference. If we look at the gravitational field is r squared. And that gravitational field, when it goes out from mass, it goes out in 3 dimensions. It goes out in the shape of a sphere. And it goes out in 3 dimensions, and it goes over a surface area of a sphere. And of course, the surface area of a sphere is calculating using r squared. The same thing for the r squared in the electric field. It goes out in 3 dimensions. It makes the shape of a sphere. You've got to find the area of a sphere, and it's got r squared in it. Magnetic fields don't do that. Magnetic fields don't go out in 3 dimensions in the shape of spheres. They go out in 2 dimensions in the shape of a circle. So since the 3-dimensional shape has a squared measurement, a 2-dimensional shape will just have a 1. So there's not r squared, it's just r. So that's sort of one of the key differences between the expressions. Now, of course, the only thing we're missing is a constant. Now, the constant is not G, it's not K. The actual constant for magnetic fields, it's going to seem kind of weird, is actually mu naught over 2 pi. And mu, that's the micro symbol, and that's not, it's like a little origin O type thing. And that stands for the permeability of free space. If you remember from electric fields, the K value was actually 1 over 4 pi epsilon naught. Epsilon naught is the permittivity of free space. Magnetic fields have the permeability of free space, which is the mu naught. Now, mu naught is equal to 4 pi times 10 to the negative 7. And one of the nice things about it, though, is you take that 4 pi times 10 to the negative 7 and you put it in there, and then you divide by 2 pi. The pi's cancel out, and one of the 2's cancels out. And you're sort of left with like a shortcut version which is just 2 times 10 to the negative 7 I divided by r, which is a really nice shortcut version that people often use to calculate the magnetic field, because punching this in is often, well, it just sucks. And some calculators don't even like having the pi and the scientific notation side by side. So you actually have to type the pi in first for some calculators. It's just really annoying. But most people just go to the negative 7 I over r to calculate how strong the magnetic field is from a wire. So it's a really, really, really simple expression. It's actually, I think, easier than the other ones you guys have done to calculate fields. It's pretty straightforward. So, for example, suppose the current here, maybe we have 0.12 amps of current running through it. And suppose, this location is, let's go with maybe 3.2 centimeters away, and we want to know the magnetic field there. Well, we would just use the expression to be 2 times 10 to the negative 7. The current is 0.12. And then divide the radius, of course, that has to be in meters, and then we can calculate the magnetic field. And we get 7.5 times 10 to the negative 7 Teslas. If you remember from grade 11, the unit for magnetic field is Tesla. And that's it. That's how you can calculate the magnetic field from a wire. It's relatively straightforward. Now, the other thing that we often find magnetic fields for are loops of wire. So we talked about this also in grade 11. We often take loops and coils of wire to make really, 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 really strong magnetic fields. When the currents are going around here, you can get some really strong magnetic fields and stuff like that. We looked at this type of thing last year. And we can find the magnetic fields for that type of stuff as well. So like ring type structures, not really solenoids, won't get into that, but for ring type structures, we can calculate the magnetic field in the middle of those. Now really, this is just a modification of a wire making magnetic field. There's no real difference. So it's just a modification of the formula. I mean, this coil is literally just a straight wire wrapped round and round and round and round and round and round and round. So when you take a wire, when you take some kind of just regular wire and you just take it and you bend up the sides to make a loop out of it, it's just a modification of the wire. Therefore, you literally mathematically just modify the expression. And we're not going to go through the full derivation or anything like that, blah, blah, blah. But to calculate the magnetic field from a loop of wire, and I like to put a little L down there for loop, it's mu naught I over 2r. And that's how you calculate the magnetic field for a loop. So it's very similar to the first expression. Most people don't use the shortcut version for this one because you don't have the pi in the denominator. It actually disappeared in the derivation using calculus and that type of stuff that you guys haven't taken yet. But that's how you can calculate the magnetic field for a loop. Now, the only thing that we slightly adjust is it's really common to have a n, where that tells you how many loops you have, because it's rare to have one loop. Sometimes you have like 5, 10, thousands of loops of wire, and every single one of these loops of wire will create a magnetic field, and then it compounds it and makes it really, really strong. So again, let's do something really simple. Let's take this guy over here. Suppose we've got let's say we got 60 loops, and let's say again we got like 0.12 amps. And let's say the radius is 3.2 centimeters. We'll just use the same values up on top and so how this works. Now for this, we got a little bit different because we don't have the canceling out shortcut version. But we've got the end value, that's 60. So there's 60 loops of wire. The mu naught is 4 pi times 10 to the negative 7. Should write that properly. So that's times 10 to the negative 7. The current is 0.12, and then you just got divided by twice the radius, or just the diameter of the circle, and you will have the magnetic field inside the middle of that loop. And let's see, that should give us about 1.4 times 10 to the negative 4 Teslas, okay, which is considerably more than what we had here. So you can see that, making it a loop makes it stronger. Then you add a whole bunch of loops to it, you get a way stronger magnetic field. So these are our two expressions. We've got, magnetic field from wire, mu naught I over 2 pi r. Most people just use the shortcut version. And then we've got magnetic field for a loop, n mu naught I over 2r. And they're relatively straightforward. They're not complicated. They work out pretty well. And we'll use those to calculate fields, and then we'll incorporate forces into that as well. But that's basically it, those two expressions. There's also, for solenoids, we don't do solenoids really, but if you have a solenoid, like more of a tube set of wires, you can actually calculate the magnetic field for a solenoid, and that's actually mu naught Ni. Mu naught's the same mu naught. The N is actually the number of loops per unit or per meter. So you actually take the number of loops and you divide it by how long the solenoid is, and then you multiply it by the current. But we don't really work with that expression really. We'll just do some wires and a little bit of loops, and we'll be good to go. Okay, so we'll start practicing in the next video, and that's it for finding magnetic fields.